Hello, everyone. Today's lesson is called Graphs That Enlighten versus Graphs That Deceive. So we'll start with some graphs that enlighten. So a graph that we'll use is called a dot plot. Dot plots consist of a graph of quantitative data, in which each data value is plotted as a point above a horizontal scale of values. Dots with equal values are stacked on top of each other. So it displays the shape of the distribution of the data. It usually possible to recreate the original list of data values, and it highlights the outliers. So here I have an example of possible pulse rates. So we can see some outliers. A pulse rate of 10 is quite scary. That would be considered an outlier. We can see that we have a dot at 40, maybe a dot at 42. So I could start to recreate those values. And then these dots that are stacked on top of each other mean a bunch of people had the same pulse rate. So let's say it's 66 is that maximum value there. So a lot of people reported 66 as their pulse rate. So that means we just keep stacking a dot on 66. So that's one graph. That's a good representation of data. If we use this same data set, interpreted another way, we have what's called a stem plot, or sometimes stem and leaf plot. It's called. This represents quantitative data by separating each value into two parts. The stem is the left digit, and the leaf is the right digit. So it still shows the shape of the distribution of the data. It's a lot easier to retain the original data values because they're just listed out. And it puts all of the data in order. This is a nice plot to use. So I can read off the values from this table. 40 and 42 would be those first two values. And then I highlighted pulse rates of 90, 92, 94, 96, and 96. So if there's a repeating value, as we can see, 64 and 66 repeat a lot, we can see that this is probably normal. We have low frequencies around the 4 and 5 stems, and 9 and 10. So at the beginning and end, we have low frequencies. In the middle, we have high frequencies. So it's easy to see the distribution of the data. These first two, very similar, about the same, seeing the distribution of the data. The only thing that's slightly better with this stem plot is we can see those exact values. I'd have to estimate a little bit with the dot plot. Right. Let's move on. Another good graph we can use is what's called a time series graph. A time series graph is a graph of time series data, which are quantitative data that have been collected at different points in time, such as monthly or yearly. So we use this if we want to see a trend over time. So let's say every year we're going to make a measurement, and then we plot the point for each of those years. So when we're using a reference of time, oftentimes we're going to use a time series graph. So in our example here, we have the years 2006 to 2017, and each dot is going to represent the value of PC shipments in the millions. So we can see each of those yearly points, and then we're going to connect them with a line. We can still see how trends change, but it's not going to have some of those values from the last two where we can see frequencies. So this is more when we see a time, we want to use time to analyze a trend. We use time series graph. Another good graph is a bar graph. So bar graph uses bars of equal width to show frequencies of categorical data. So similar to the histogram, but here we have categorical data. So that's the important piece here. We use it just for categories. We have a more specific type of bar graph for categorical data. with the added stipulation the bars have to be ordered in descending order. So here we don't have a Pareto chart, we just have a normal bar graph. So here in our example, we still have frequencies, but causes of fatal plane collisions is categorical data. There's no numerical value, so it's categorical data. So it's just like a histogram, but with categorical data. So it still has our frequencies, but pilot isn't a level of measurement. It's not a number. Pilot error is just a category. Mechanical category. Sabotage category. Weather category. Other category. No numbers involved. Okay. A commonly used graph is a pie chart. It's a very common graph that depicts categorical data. So we've made a little bit of a switch here on these last two. These are used for categorical data, not quantitative data, in which the size of each slice is proportional to the frequency. So I took the same data in the left one, made it into a pie chart. This one's a little bit easier to read. You can see most of the pie is because of pilot error. So it shows the distribution, and this is quite common. I'm sure we've seen pie charts before. What we might have not known is this is only for categorical data. Okay. So here are two graphs we do not want to use, so graphs that deceive. So a common deceptive graph involves using a vertical scale that does not start at 0. So if we look at my first set of graphs here, if we look at the first one, we start at 10% on our vertical scale, and it looks like there's a very big difference between the drug and the placebo. We look at the second one, where we started at true 0, we can see maybe there's not as much of a difference as we thought. So starting a vertical scale at a number greater than 0 can really skew what the conclusion actually says. So this is a common tactic actually used when you want to have a conclusion that the data doesn't match. Not the most ethical way to do it, but it probably commonly is used. And then our next type is pictographs. These are very rare, but it is a type of graph that deceives. So in this case, we have dollar bills to represent the subway fare. Bigger dollar bill means bigger price. This doesn't give us too much information if I took away the context between small dollar bill, big dollar bill. Not that helpful of a graph. So all of the other ones we saw are good graphs. Some meant for quantitative data, some meant for categorical data. These are graphs we want to avoid. We always want to start our bar graphs or histograms at true 0. Okay, so that's going to be it for today's lesson. Next time we'll talk about scatter plots. I hope everyone has a great day, and I'll see you all next time.